So we finally get to put it all together. We're actually going to start testing claims, testing hypotheses. In section 8.3, we'll be testing hypotheses that involve proportions. In 8.4, means. And 8.5, means. The difference is in 8.4 you'll know sigma, and 8.5 you won't. Very similar to chapter 7. Proportions, means, knowing sigma, means not knowing sigma. So that is the idea here. So right now today we're talking just about testing claims that involve proportions. Proportions for us mean percentages and, well, proportions. So if you see something like 35%, that's a proportion. That's a proportion. Let's say 35% of the people are blonde. Bam, proportion. If we see 0.20, it's talking about a proportion of 20% there. That's a proportion. Or most. If you ever see the word most, what's most as a proportion? 50%. Equal to 50, greater than 50, greater than equal to 50? More than 50 is most, more than 50%. So that's also a proportion. So this is our arena for this section right here. Is it dealing with means? No. No, that's going to be another section. Right now we're just dealing with proportions. Here's our requirements. They are going to be the same exact requirements that we had for chapter 7 when we talk about proportions and confidence intervals. So the same requirements apply. Those requirements were, well, number one, you got to have a random sample. That pretty much goes without saying in this class. Number two, if you remember this, n times p and n times q. Do you remember what p and q stand for? Probability of success and failure, or the proportion of success and failure. And n stands for your sample size. So this was one of those requirements from chapter 7. We rarely checked it because it worked out on our problems most of the time. Is there cases where it doesn't work out? Yeah, and then you can't use this stuff. For us, it's going to work out most of the time. And third, you've got to be able to find your n. What was n again? I just said it, but what was n? You've got to be able to find your sample size. So n is our sample size. Or in other words, for proportions, it could be the number of trials. Those are one and the same. You've got to be able to find your p hat. How do you find your p hat? Is p hat ever a number like 10? No. Is p hat ever a number like 634? It's x divided by n, which means that you are always going to get some sort of decimal. Because, hey, you're dealing with proportions. Whenever you see that p hat and the lowercase letter p, you're talking about proportions. Right? So when we have p hat, if you plug in a whole number here, you're doing something wrong. Right? So if you're getting, oh, p hat's got to be 634 because there's 634 successes. No, 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 no. No, p hat is found by taking the number of successes divided by the number of your sample size, or trials. How many things you were looking for divided how many people you surveyed. That's the idea here. Are you guys okay that p hat is never going to be a whole number? It's always decimal. So we need to be able to identify p hat. Also, we need to know that p, that lowercase letter p, is the population proportion of course, the p hat was our sample proportion. That's where we're getting that from. And q. Here's a big thing with q, because people sometimes make a little mistake on this. Is this q based on this p hat, or is it based on this p? Based on p. Yeah, that's why it doesn't have a hat. 1 minus p. If you can find that stuff out, then we can find our test statistic. This is going to be the same test statistic I gave you last section. Some of you probably found your test statistic on your homework, right? Didn't ask you to do that a lot? The test statistic you should have found for proportions was a z. It was a z test statistic, and it was, as a matter of fact, p hat minus p, all divided by this big square root where you had p times q over n. P times q over n. Does that look familiar? You probably should have worked with that if you did your homework, yeah? All right, so it's the same thing. Can we find p hat? Yes. for any value, it's either going to be directly given to you. Let me make a little note here, or you make a note or something. It's either going to be given directly to you. It could say something like, we found a sample with 35% of something. We found a sample where the proportion was 0.20. We could find samples like that. So it could be given directly to you, or like on some of your homework, you might have had to find it. If I said 634 out of 1,000 people felt this way, well, your p-hat's not 634, it's 634 divided by 1,000, or 0.634. Are you following this? The p, that's going to be given by your claim. Somewhere in your claim you're going to be finding this because you're making a claim about the population. This deals with the population. Remember, the whole idea here is these deal with the population, this deals with your evidence, your sample. So you're comparing your evidence, your sample, to the population claim and seeing if it's close enough to make it right. Do you have kind of the idea here? I hope so. We're going to do some examples so it'll become very, very clear, but that's our idea. Also, one more thing, this p, is this p a p-value? Or is it a proportion? A p-value is that capital letter P stands for the probability that's associated with a test statistic. So we can find a p-value later, but it's not a proportion. I know it's confusing, there's two different p's going on. Actually, there's three different p's. There's p-hat, a p, a backwards p, which is a q, and then we have a big letter p, which is a p-value. So, all crazy stuff. Are you ready for an example? We're going to do the two different methods. I'm going to try to put them side by side, but I'm at the race this stuff and do it. Do you guys have any questions on this stuff? Okay, this is actually all old news. This is old notes for you, just now being applied to our hypothesis testing. So, one example, I'll show you the traditional method and the p-value method. I'll show you the p-value method first, and then the traditional method second. You ready? You excited?
Yes.
Yeah, okay, good. I was hoping for a lot more excitement because this is where we're trying to get to in this whole class. This is it. We did all that other stuff to get to this point. All of this stuff is literally irrelevant if you can't put it all together right now. In a sample of 300 corporations, (183) of the CEOs were male. You're gonna see that this is very similar to some of the things I was throwing at you in the previous sections. The male CEO thing, right? Well, now we're going to be able to test this statement for ourselves and see what's going on. So, out of 300 corporations, 183 of the CEOs were male. We are going to test the claim that most CEOs are male with a 0.05 significance level. Now, all the information is quite pertinent. You're going to be using everything up here, you just need to know where to put that information. So when you read your sentence, I mean, you should use all those numbers. So, I mean, unless I put something stupid like cats are pretty, you're going to be using everything up there in your problem, all right? So don't leave anything out is what I'm trying to say. So, in a sample of 300 corporations, 183 of the CEOs were male. Test the claim that most CEOs are male, use a 0.05 significance level. That's all you're going to be given on your test, right there. I'm going to tell you next to either use traditional method or use p-value method. That's all you're given. So you really need to know what to do on this on your own. Now, I can give you some clues. Everything that you need is up there. I give you some clues on how to determine this. First, you start with, am I dealing with proportions or means? Which one?
Proportions.
Well, of course, we're in the proportions section, sure, but you're not going to have that on your test. So what tells you you're dealing with proportions? Firstly, does it say anything about means? Does it give you something out of something? That's a pretty good indication right there. And then the claim. The claim is what's going to tell you what you're testing. The claim will say something about means, or will say something about some type of a proportion. What's the proportion here? With most. Most right there tells you something. It says, oh, most means I am dealing with a proportion. That's why I underlined most when I introduced this section to you just a couple minutes ago. We're definitely dealing with proportions. I'm going to show you the two methods right here is the p-value method. Over there, I'll show you the traditional method. Same example. We'll get the same result. Bless you.
Thank you.
If we're going to do the p-value method, the steps are literally identical. We're going to have 7 steps. I want to see all 7 steps from you. Our first step when we're doing this, we're going to put everything together now. The very first step was you got to write the claim and the opposite of the claim. Do you remember doing that? You have homework assignments just on that. So step number 1 is claim and the opposite. Let's go ahead and let's see if we can identify the claim and the opposite. So you're gonna read through this. Almost every one of your questions are going to say test the claim that. Hey, hint, hint. That's where your claim is. So test the claim that. What are we testing the claim? Most CEOs are male. Now, did you say we're using a proportion or mean? Are we testing proportions or means here? So you got to use the right symbol, right? Are we going to use a mu? That would be for means. You have the symbols in your head. What are we going to use? Now we're going to use p hat or p for our claim. P. Very good. You're testing a claim about a proportion. Very good. P hat would be for sample, right? We're going to have a p hat, but that's based on our sample information. The claim will always have to do with a population parameter, either proportion mu, p, mu or p. So p. How do you signify that most CEOs are male, or that the proportion greater than, not equal to, right? Most would be more than. How much? Perfect. Perfect. That's the claim. So far, so good? Now state the opposite of the claim. You're still going to have a p, you're still going to have 0.50. What are you going to have here? Fantastic. That's step number 1. Step number 2 is an easy step. Step number 2 is you're supposed to identify which one of these is h sub 0 and which one of these is h sub 1. Which one is h sub 0, the claim or the opposite? Wait, which one is h sub 0, the null hypothesis, the claim or the opposite?
Opposite.
Good, because the h sub 0 has to have the equality portion to it. So this is h sub 0. That makes this one h sub 1. The equality is h sub 0. So you're simply going to rewrite that in step number 2. Remember, this idea, this is one of those times where I tell you, you got to do it this way, right? And if you don't, you're probably going to get it wrong. If you do, if you follow my steps, you're going to get it right. If you follow them and you know how to determine between proportions and means and z-scores and t-scores. Those are the 3 keys. Follow my steps, be able to determine between proportions and means, z-scores and t-scores. That's it. So h sub 0, we're going to write that one out. We're going to write h sub 1. H sub 0, do I write this exactly like it is for h sub 0? What do I write? That's kind of something we always do in this day and age with our h sub 0. We always have the equality, and the reason is because later on when we come up with our test statistic, which we're going to find in just a minute, that tells you how much p is equal to. So we look right there, it says, oh, it's equal to 0.50, we don't have to guess about it. The h sub 1, you never, ever change that. So that's step 1. Step 1 is the claim and the opposite. Step 2 is identify h sub 0, h sub 1, and simply rewrite them. How many people feel okay with the first 2 steps? Okay, step 3 is also a pretty easy step. First 3 steps are not bad. Although you do have to get this right, otherwise your whole problem's going to fall out behind you, right? If you mess this part up, you're done. It's not going to work. So be real good at finding those claims. You got to find your alpha for step number 3. Can you tell me what is your alpha for step number 3? What's alpha? Good. That has to do with our significance level, and it will be given to you. So far, so good? Step 4 is where you actually do the math work. This only place where you actually have to do math work besides looking numbers up in a table. Step 4, you're going to calculate the test statistic. That means use this formula. The one I put on the board earlier. So step 4 continued. Let's go ahead and find that test statistic. We need to be able to identify p hat. We need to be able to identify p, q, and n. So let's work on p hat first. How much is our p hat? Is our p hat 183? Our p hat is going to be a sample proportion. It's based on your sample. That's why we have the p hat. It means sample proportion. How do you find your p hat here? Perfect. How much is your p hat? 0.61? Rounded? Or is that it? Sweet, I like it. It's easier. 0.61. You okay on finding p hat? P hat's never a whole number. P hat's always decimal, between 0 and 1. That's what a proportion is, by definition. Okay. Now, if you look back at our formula, we've got our p hat, but we also need to find p, q, and n. These p's, by the way, are the same p's. Hopefully you did that on your homework. You had the same number here and here, yes? Same p. What is our p here? What is our p here? It's already written on the board for you. So that's why I give you these steps in this order. I don't ask you immediately for the test statistic, because you have to do some legwork to even find it. You got to do the claimed opposite. You got to do the h sub 0, h sub 1. You got to do your alpha. Then you look back at your h sub 0. You look right here, and you read what your h sub 0 equals. It says p equals 0.50. Guess what? That right there tells you what p equals. How much does p equal? It's even on the paper. That's why we write it with the equal sign. So p equals 0.50. You're basically just restating your null hypothesis. That's the thing you're testing. It's got to go in there somewhere. If p equals 0.50, how much does q equal, please? Those things are tied together. It's one minus the other. It gives you whatever you're looking for. So, okay, and the last one, how much is our n? Good. That's our number of trials or our sample size. I mean the same thing in this context. Would you raise your hand if feel okay with those numbers? Now, I want you to plug them in right now and see if you can come up with the z test statistic. So 0.61 minus 0.50 divided by the square root of this big information. 0.50 times 0.50 divided by 300. Remember, you're not supposed to round until the last step. You're dealing with proportions, which means you got to be accurate to at least the third decimal place. If you round, that's not going to happen. I'm sorry, z-scores, 2 decimal places. Number and then 2 decimal places. So you're going to do 0.50 times 0.50, that's going to give you 0.25. You'll divide by 300, whatever that gives you. Then take the square root of that number and divide 0.11, that's 61% minus 50%, 0.11, divided by whatever you had. Let's have a z-score for me, please.
3.81.
3.8 what? 1. By show of hands, how many people have a calculator? Raise your hand if you have a calculator. Good. Now keep your hands up. Keep your hands up. How many people were able to find that if you have a calculator? Good. That's everybody. All right. If you weren't able to find that, you don't have a calculator, you need to see me later to figure that thing out. If you can't do it on your own. Are you okay with the first 4 steps? So claim opposite. Check. H sub 0, H sub 1. Yep. Alpha, got it. Test statistic, no problem. I'll give you a little clue here. These are the same exact 4 steps for the traditional method. You do the same 4 things over and over and over again. But here's where it changes. In step number 5, we're going to draw a picture. Now, all of your pictures are going to look the same. When I say draw a picture, I mean that. That's your picture. It's very original. Here's what you do for the p-value method. Your picture's going to look identical in step number 5, but what you put on your picture will be different. In the p-value method, what you do is you place your test statistic. This is the test statistic right here. That's what step number 4 says, test statistic. This is the test statistic. You place this on your chart. So go ahead and place that on your chart right now, 3.81, is that what it was? 3.81. Zero's in the middle. Where's 3.81? Stop me when I get there. Somewhere over there. Does it have to be exact? $3.81. You okay with this one? You sure? 3.1. Okay. Are we dealing with a left-tailed, a right-tailed, or a two-tailed test here? Right-tailed. It's clear because we have that in the right tail. That's the area that we're looking at. So with a p-value method, sure, you're going to have some sort of a tail on this thing. We're looking at a right tail. We're going to find the area in the tail. So p-value method, you put your test statistic on your standard normal distribution. This is our test statistic. And you find the area in the tail. This is called the p-value. P-value is the area in the tail, or the tails for the given test statistic. So you need to know whether we're a left tail or a right tail test. This, of course, is a right tail test. That's why we have... By the way, I'm sorry, I skipped that. How do you tell whether it's a left tail, a right tail, or a two-tail test? How do you tell? Good, we look right here. This right here, H sub 1, says you are going to the... That's a right tail test. You okay with that one? So this way, the less than would be a left than. That's a less than would be a left tail test. Greater than, that's right. That's a right tail test. If I had the not equals to sign, that would be a two-tail test. And you would have to split this up. And you have 3.81 here and negative 3.81 over there. You get me so far? Okay, so this is a right tail test. That's why we only have one test statistic, and it's on the right-hand side. How many people feel okay with that so far? Good. With this method, your positive and negative should match a right tail versus a left tail test. It should match that. A two-tail test won't exactly work that way. A two-tail test, you have to put it in both spots, so you need to be very good at telling a left tail, right tail, two-tail test. Can you do that? Are you okay with this? That's a right tail test. We only have one test statistic here. Okay. Then we find the area in the tail for the given test statistic. So right now, on your calculator or on your table, I don't care what you use, find me this area. Go ahead and do that now. We're here. I just wrote down the next couple steps to talk about in just a moment, all right? Firstly, on your table, you should be looking up 3.83, right? Is 3.83 on your table? It says for any value bigger than 3.5, you're supposed to use what? 0.99999. So, is our area 0.99999?
No.
Yeah. How much is it?
0.0001.
Again, you got to be smarter than the table, right? This table only gives you areas to the
Left.
This is 0.99999. No, I'm sorry, 0.9999. I don't know if it's the other 9. Probably not. It's probably 0.99996 or something. 36? Whatever it is. Okay. Anyway. On your calculator, you would put 3.81, comma 10 if you wanted to use your calculator, and that would give you the direct area. Are you okay with the calculator work? On your calculator, 3.81 to 10, because 10 is like the limit where it even matters. And that's going to give you this area directly. On the table, it's going to give you this when you look it up. However, you're not going to put 0.99999 because that's not what this area is. This is 1 minus that. So our area is 1 minus 0.9999. That's 0.0001. That's our area. That means it's a p-value. P-value stands for probability value. The probability you're going to get a value over here. That's the p-value, probability value. Is it a proportion? Ladies and gentlemen, is a p-value a proportion? Nope, it's probability. The p-value stands for probability value. It's the probability of getting some score over this way. Not this way, this way. Are you guys okay with doing the p-value, finding that value? Does it seem familiar to you? This is why we did all of chapter 6. Right here is so you could do this. So you could look that up on a table. That's it. That's why we did it. Now the question is, how do you make a decision? Well, a decision is made by comparing your p-value to your alpha. What's our p-value again, ladies and gentlemen? Right here. What is our alpha, please? And you've got to put one of these two symbols here. You've got to put a less than or equal to or a greater than. What's this? This is our p-value, by the way. This is our alpha. Which one's bigger? 0.05 or 0.0001? So is it greater than or less than? Less than?
Yeah.
Less than or equal to. You got to use one of these symbols. It's less than or equal to or greater than. So we're going to choose a less than or equal to. Is that true? Is 0.0001 less than or equal to 0.05? That's something you should be able to determine. Is 0.0001 less than or equal to 0.05? Yeah, it's actually strictly less than, so it's even stronger than this statement, but we have to write one of those two symbols. From there, that's where you make your decision. So check it out. Are you going to reject h sub 0, or are you going to fail? This means fail to reject. Or are you going to fail to reject h sub 0? Let's check it out. If the p-value is less than or equal to alpha, you reject. If it's greater than alpha, you fail to reject. What are we going to do here? Reject or fail to reject?
Reject.
We're going to reject. Why? The p-value is less than alpha. Reject h sub 0. So claim opposite, got it. H sub 0, h sub 1, no problem. Alpha, very easy, it's given to you. Test statistic, it's the only place you do math. Right there. That's it. That's math. You get your test statistic. With a p-value method, this is where it changes. Traditional is going to change after this. With a p-value method, you put this on your chart, and you look up the area in the table, depending on whether you're a left tail or a right tail or a two-tail test. Nod your head if you're okay with that. You know left tail, right tail, two tail. You look up your area, that is your p-value. You compare the area in the table, your p-value, to your alpha. If it's smaller than alpha, you reject the h sub 0. If it's not smaller than alpha, you have to fail to reject. Here's what this says in plain English. This says that this sample data is far enough away, is rare enough to prove my assumption incorrect. That's what it says. If my assumption's proved incorrect, the alternative is true. Now this is where this comes in, where you had to add a step. Which one Which one was false? What did we reject? Did we reject h sub 0 or h sub 1?
H sub 0.
So we rejected this. That means that this one is true. Which one was h sub 1? Was it the claim or the opposite?
The claim.
That's why we label it. So when you reject this, you know, oh, I accept that. Did you prove your claim right? Yes, you did. You certainly did. It said you reject h sub 0. Rejecting h sub 0 means h sub 1 is true. So reject h sub 1, or h sub 0, h sub 1, true. Depending on where h sub 1 is, that means you prove your claim or your opposite. So we just proved our claim right here. So what this means is that if our claim is most CEOs are male, we just proved that. We just proved with statistics that most CEOs are male. It wasn't an assumption that we have right now anymore. It was based on evidence. We tested it against a claim. It turned out to be true. So here's how you interpret this. If you reject your h sub 0, that means that your h sub 1 is right. If it's listed as your claim, it says you have enough evidence to support the claim that, and you restate your claim. If you fail to reject h sub 0, you say there's not enough evidence to support the claim that. So it's either this one. If you reject h sub 0, you're going to write exactly this. If you fail to reject h sub 0, you write exactly this. So reject h sub 0, here's what I want to see on your paper. There is enough evidence to support the claim that, and then you're going to state the claim. In our case, most CEOs are male. If you don't write the interpretation, this class is useless to you. If you don't know the interpretation, it means that you can do all the work, but you still don't get it. It's just it was a waste of a semester. Okay, honestly, if you can't do the interpretation, because right now you need to be making decisions about this data. If you can't, if you just do this and you go, I can find a test statistic, don't care what it means. I know I reject the hoe. That sounds pretty bad. I know I reject the h sub 0, but I don't know what that means as far as the statement goes. You got to be able to get the interpretation. That's what this class is about. That's why this class isn't hard mathematically. It's all based on your calculator. The math isn't the hard part. It's not the calculator. It's interpreting. This is a word problem. This is a critical thinking class. Well, there's a writing component. There should be a writing component to it. You got to write stuff out and understand it. So you're going to write, if you reject the h sub 0, there is enough evidence. That means you had your sample. It was rare enough to say your claim was wrong. Or to say, I'm sorry, say your null hypothesis is wrong. That means your alternative hypothesis is right. If the alternative hypothesis is stated with your claim, that means your claim is right. If not, if you couldn't prove that wrong, then you can't prove that right, then you can't prove your claim right. Which means here, if you fail to reject h sub 0, if you fail to reject it, that means there is not enough evidence to support the claim. That's the only two cases you have. It's either you're going to reject or fail to reject. If you reject, great. There's enough evidence to support your claim. If you fail to reject, there's not enough evidence to support the claim, and then you restate your claim. That's all there is to it. If you can grasp this concept, then you have hypothesis testing down. In the next two sections, 7.4 and 7.5, all we're going to be dealing with is means rather than proportions. But this is the idea. These are the same 7 steps no matter what you do for the p-value method. Are you okay with the 7 steps? How many people feel pretty good about it right now? Good, that's great. Would you like to see the comparison to the traditional method? Okay, traditional method, steps 1, steps 2, step 3, and step 4 are identical. So I'm only going to start step number 5. You okay with that? Yes, no? 1 through 4, same. So we're going to start with step number 5 for the traditional method. 1 through 4 will be identical in either case. You still have a test statistic. Here's where it deviates. It's only one little thing. Just it. At step number 5, instead of finding the p-value, instead of putting the test statistic on your graph, what you've got to do is determine whether you're a left tail, a right tail, or a two-tail test and find the critical value. Notice how we didn't even have to find a critical value for p-value method. That's why people tend to use it, is because you don't have to find that. So with the traditional method, the way people used to do it all the time, you're going to find a critical value. The critical value is still based on your alpha. So you need to determine firstly left tail, right tail, two-tail test again. What were we? Left tail, right tail, two-tail?
Right tail.
Right tail. So that's over here. Again, it doesn't have to be like to scale or anything. And instead of looking up this area, you're going to go in reverse. What you're going to do is, since that's a right tail test, your alpha is in that tail. How much is your alpha? Notice that if we had a two-tail test, we'd have to split up our alpha. You still okay? This is 0.05. So here's the big difference. You ready? With a p-value test, you look up your test statistic in the z-score section and you find an area. With the traditional method, you look up an area and it's going to give you a critical value that's still a z-value. So right now on your table, I need you to look up 0.05. Remember, 0.05 is an area, so look up 0.05. You should probably get something like 1.645. Actually, you get negative 1.645, don't you? But now this is the part where you're going to be smarter than your table. You're going to look at that and you go, okay, if I'm talking about a right tail test, can that possibly be a negative number? No. So what value is that? 1.645. Now this is not a test statistic, this is a critical value. With the traditional method, you're going to have something called a rejection region and a fail to reject region. This is the number that separates those two things for you. Which one is the rejection region, the right or the left? It's the area in the tail. That's what we're looking at. So this is the fail to reject, and this right here is the rejection region. So if it falls here, you don't reject it. If it falls there, you do reject it. So step 5, we draw our picture. It looks identical, doesn't it? It's still a right tail test, isn't it? It still has a line there. It's just the line is a different thing that we're talking about. I hope you're still with me on this. The p-value, you put down the test statistic, you find the area. You get it? Traditional is opposite. You put down the area, you find the critical value. It's literally doing the opposite thing. That's why on your chapter 6 stuff, I had you not only look up z-scores, hey, p-value, I had you look up areas, hey, traditional method. That's why that's why I had to be good at that stuff. So you're looking up a critical value here, and then what you do in step number 6 is you compare the test statistic to the critical value. So one method you're comparing the areas. The other method you're comparing the z-scores, or the test statistic to the critical value. there's two options. You can be in the rejection region. If you're in the rejection region, hey, you're going to reject. Or you can be in the fail to reject region. In which case you fail to reject. But in either case, we're talking about H sub 0. Let's see if we can do it. What's our test statistic? Is it different than over here? Would you have a different test statistic with traditional versus p-value? Test statistic. No, you're going to calculate this exactly the same way. It's still going to be 3.81. So what you're going to do now is you're going to say, okay, where is the 3 point? Is that right? Where is the 3.81? Is it in the fail to reject region or is it in the rejection region? It's like way over here, right? 3.81 is there. That's in the rejection region. So now you make your decision. Are you going to reject H sub 0 or fail to reject H sub 0? Why? So here's what this says, okay? This is the same idea. Please watch on the board here real quick. What the p-value method says is, this is how rare you need to be, this or smaller. Are you listening? This is how rare you need to be to prove this right or wrong. This is how rare you are. That's rare enough. Here's what this says. This is how rare you need to be to prove this right or wrong. Anything past this, you're rare enough. This says I'm past that. That means I'm rare enough to prove right or wrong. It's the same exact idea. One's just comparing areas. One's comparing the critical value and test statistic, which gave you those areas. That's it. So in this case, yes, you're still going to reject H sub 0. If you reject H sub 0, that means you accept H sub 1. And you're going to get the same exact interpretation. If you reject H sub 0, there is enough evidence to support the claim that most CEOs are male. Step 7 is the same. Step 6 is just slightly different. It's really step 5 in combination with step 6, which is the different thing. Okay, by a show of hands, how many people were able to follow that? Was that a good explanation of the difference between those two? If you need more clarification, watch that video and come and see me because you are going to know how to do both of them. Now, we're going to start one more example. We're going to work it together, but I'm going to have you do most of the work. Because really, I mean, I know how to do this. I wrote the test, shoot. But you are the ones who are going to have to do this on your own, okay? So we're going to do, I'm going to have you use the p-value method on your own. Then I'll show you the difference between that and the traditional method. Do you guys like peas? I love peas. I eat peas like every single night. A little butter, fantastic. Mashed potatoes, oh, so good. Have you heard about genetics that deal with peas? And it's like the pea pods and the green and the yellow and all that stuff? Is it like some guy named Mendel, wasn't it? Mendelian genetics, whatever they call that. We're going to find out about peas. Let's say that in our example here, they got a whole bunch of peas. And the pods on these things, there are 428 green pods, 152 yellow pods. I want us to use a 0.05 significance level to test the claim that the proportion of yellow pods is equal to 1/4. we're going to use the p-value method first, and then of course I'll show you the traditional method after that. The only thing we're going to do today in class is that we're going to do the claim, the opposite, determine which one's h sub 0, h sub 1, and do the significance level. Your homework is going to be to finish that problem, okay, with the p-value and traditional. I want to see both on that. You got it? That's going to be your homework tonight. So, when we're talking about our step number 1, the claim and the opposite, the first thing you need to identify is whether we're talking about proportions or means. There's only two choices. What are we talking about, proportions or means? Proportion. Yeah, clearly, because it says proportion, right? That's kind of nice. So we're going to have to state the claim, and it's going to have a p in it, because that's the population parameter we're talking about. How do I state the claim? It says, state the claim, or test the claim that the proportion of yellow pods is equal to 1/4. Equal?
Yeah.
Equals 0.25. It's got to be a proportion. You all right with that? We're not talking about most, right? We're talking about the proportions equal to 1/4. Proportion equaling 1/4 would be equal to 0.25. Raise your hand if you're all right with that. Okay, you guys over here, yes or no? You sure? All right. State the opposite of the claim. What's the opposite? Which one's h sub 0? Claim is opposite. Which one is h sub 1? Well, it's given to us. So the opposite, sure. Now, step number 2 is simply to rewrite that. So we're going to have h sub 0. It's already got the equals. That's great, 0.25. h sub 1, we have the not equals, 0.25. That's the opposite of that claim. Step number 3 is to find your alpha. Can you tell me in this case, how much is your alpha? Sure, 0.05. Are you okay with the alpha there? The first 3 shouldn't be that big of a deal. We have our claim, proportion equals 0.25. Opposite, not equal to. h sub 0 is our claim in this case. h sub 1 is the opposite of our claim in this case. We rewrite that, we state our alpha. Step number 4 is you're going to find your test statistic. You're going to do that on your own at home. However, I want to make one point for you. P hat. When you find P hat, we're talking about the yellow pods, right? How many yellow pods did you have? Now the key here, how many pods total do you have? Really?
No.
That's 428 green pods. How are you getting 580?
Because you add them.
Ah, there's green and there's yellow. If you combine them, you've got 580 total pods. So that number is 580. So read the problem carefully on that one. You're not divided by 428. That's going to be way off. You divide by 580. That's going to give you a proportion. And you find out that decimal. P, of course, is given by your h sub 0. Q is given by that same thing, 0.75. N in this case is 580. 580 for your sample size because you're adding those pods together, the green and the yellow. Finish that up, do the p-value test and the traditional. Did today make sense for you? Well, let's continue working on our problem. We're trying to do a hypothesis test with the proportion. Of course, we read our problem, we come up with our claim, our opposite, our h sub 0, h sub 1. We label those out, we have our significance level, and we're on the point where we're going to find our test statistic. Now, of course, with the p-value method, what our idea is, you're going to look up the probability of that test statistic in the tail, and you're going to compare that to your alpha. If it's less than alpha, it means it's rare enough, you're going to reject the null hypothesis h sub 0. If it's not, if it's bigger, then you don't have enough evidence to say anything about your claim whatsoever. So that's where we're at this point. Are you guys okay on stating the claim and the opposite? Of course, we're using proportion, so we're going to use that p. Of course, and this p doesn't mean a p-value, it means a proportion. In this case, it's a lowercase letter p. Where we have our equal sign, there's h sub 0, not equals to, well, we have h sub 1. And we're getting that from our word equals. It's not like a greater than or a less than, it's a equal to, so we got to use the equal sign. Our significance level is always going to be stated for us, so that's a 0.05. And now we're on to this part. Can you tell me how much is your p hat? Firstly, what's p hat stand for again? Clearly it's a proportion. What type? Sample proportion. What is our p hat in this case? How are you getting what would you say, 0.26? How are we getting 0.26? I don't see 0.26 anywhere up there. Okay, so our proportion of successes for the sample means whatever we're looking for. In this case, our successes are yellow pods. So we look here, we have 152 yellow pods. And we divide by the total number of pods that we've looked at. What's the total number of pods that we looked at? Was it 428 or something else? How are you getting the 580? If we add those up, that's how many pods total. Because yeah, sure, it says 428 green pods, but that's not all the pods, is it? And if we divide that 152 by 580, we're going to get 0.26. Where do we find our p? Where's that come from? So I can't afford to have you get lost right now, right? I mean, p hat, that's not too bad. We just do our division problem. Where do we find our p? Where's that stated? Yeah, that's actually right here, right? We always look there. That's going to be, that's why we use the equal sign. So it says, oh yeah, whatever parameter we're looking at, mean or proportion in this case, it's going to be equal to something. We find that from our h sub 0. So p is 0.25, making q 0.75. And n, how much is n? Good, that's all the pods that we've collected. In our case, 580. Now we calculate that test statistic. This is what I asked you to do at home. If we're going to plug all this stuff in, we have z equals, not a whole number because we're talking about proportions here, it's going to be the 0.26 minus 0.25. That right there, that 0.25, that's from, well right here, our p. That's from our statement. That's from the claim. Then we have the square root of, we use that number twice, 0.25 times 0.75, divided by whatever our sample size is or number of trials, 580. How many people got that far on their own at home? Good deal. How much did you find for your Z test statistic? Wait, how much? 0.55? 0.55?
I got 0.556.
0.556. So we'll say 0.56 since it's a Z-score. 0.56. Hey, does that mean the probability is 56%? Is that what that means right there? Have we looked up an area yet? So that's still a Z-score. Now is the difference between the p-value method and the traditional method. Up till right now, we would have done everything exactly the same. So at this point, here's the p-value method. You're going to draw your picture. You're going to determine whether we're a left-tailed, two-tailed, or right-tailed test. In our case, ladies and gentlemen, are we a left-tail, a two-tail, or a right-tail test? What are we? We're a two-tailed test. Why? How can you tell we're a two-tailed test? Okay, so if we look back at our h sub 1, if this was a less than, we'd be on the left tail. If this was a greater than, we'd be on the right tail. Since it's a not equal to, that means that you can be below or above and it still would prove our claim wrong. That's what we're looking at right now. So we're actually a two-tailed test. Now listen, I haven't showed you this before on a two-tailed test with a p-value method. I've showed it to you on traditional method, but not a p-value method. Watch carefully because it's the first time and only time you're probably going to see this with a p-value method. If you have a two-tailed test, what you do is you split your z critical value. You state it twice. One positive, one negative. Our p-value is the area associated with each of those test statistics. So, in our case right here, we're going to have to add whatever that value, whatever that area is, to whatever that area is, or whatever that probability is. So in our case, when you look up that 0.56, what are we going to have? Look up 0.56.
0.754.
Or negative 0.56. You know what, actually, it's probably better to look up negative 0.56. Look up this one, the negative 0.56. And the reason why we're looking up the negative 0.56 is because our tables will only give us area in the left-hand side. So we want to look up this one first. And can you tell me that one if you look up? How much?
0.2877.
0.2877, okay. 0.2877. Do you guys know where the 0.2877 is coming from? Are you sure? So this is our test statistic right here, our Z test statistic. The reason why we have two of them right now is because we have a two-tailed test. That's what we have to do with the p-value method. So you gotta say, well, since I'm supposed to have a left tail and a right tail, yeah, this isn't really going to be working for our left tail, but we have to put something over there because we know that our alpha is spread into two tails if you're talking about a left tail test. So you can do this one of two ways. I'm showing you a slightly different way to do this so we can compare it to alpha. Otherwise you have to compare it to alpha over 2 and that gets a little confusing. So I'll show you both ways. Are you ready to see both ways? Way number one is the way we're doing it right now. You put your test statistic here and here. We find our area here and here. That's giving us our two tails because we're talking about a two-tail test. Nudge your head if you're okay with that so far. Okay, great. Now, since you found this one, because we want the area to the left, that's what we're talking about. Look up that score. You get 0.2877. We don't want to look up this one because it's going to give us all this value, right? And that covers this part of it, which is not in our tails. How much is this? Yeah, it's symmetrical. It's what's kind of nice about this, right? You don't have to do a whole bunch of work. So 0.2877. So can you tell me how I find my p value? In this case, what's my p value? Is it 0.2877 or something different than 0.2877? What do you think? Remember, the p value is the area in the tails. So is it just 0.2877?
0.5754.
How'd you get that?
Adding 2.
Okay, so we know that p-value stands for all the area in the tail, so if I add those two things together, say that one more time.
0.5754.
0.5754 because we're going to add those are big tails, aren't they? And we're going to see what the interpretation in just a bit. And we compare that to our alpha. So whatever our alpha is, what's our alpha?
0.05.
And we have to use one of these symbols. We've got to use less than or equal to or greater than. What fits here? Less than or equal to or greater than? Clearly greater than. And then you have to be able to make your decision. Your decision's based on the comparison of p-value to alpha. So if p-value were less than or equal to alpha, it would say, oh, hey, your evidence is overturning your null hypothesis. Your evidence is strong enough to say that your null hypothesis, because that's where we got this information, right? That's what we're comparing our sample to. You with me on that? It's our null hypothesis. That's why we have the equal sign right there. We're comparing that and we're saying, well, this evidence is either strong enough or not strong enough. It's either rare enough or not rare enough. Is it rare enough here? Is it less than or equal to alpha, in other words? No. So are we going to reject the null hypothesis or not? This is where you guys got to be pretty good at it. Looking at that information and go, oh yeah, I reject it, or no, I don't. This one would be rare enough. This is where you reject. This one. This is where you fail to reject. What do we do there? Yeah. What it says is that your evidence is nowhere near, actually nowhere near, not even close, not even really close to rejecting your null hypothesis. You would say that we fail to reject H sub 0. That's our next step. Let me point something out to you at this point, because you know a lot of people, they get a little confused on why in the world do we use this number twice? That doesn't make sense. We're not even finding your negative test statistics, so why is that even on the board? Have you thought about that yet? Well, maybe you just did because I just told you to think about it, right? Well, if you think about this, you do have a two-tailed test. So what we're doing here is kind of doubling this area when you notice it, right? And it's easier to find over there anyway, which makes it kind of nice. Now, if you wanted to do this a different way, you'd have to draw your picture and say, oh, my alpha is 0.05, but that means there's 0.025 in each tail, right? So there's two ways to do it. You can either draw your test statistic twice, find the area twice, and add it together. You see that way, right? Or leave it one tail, find out that area, and then compare it to half of alpha. Why half of alpha? Because we're dealing with a two-tail test. Do you guys see the difference? See the similarity? How it is the same thing, just one's divided by 2. It's the same exact idea. That works, but this way is a little bit more confusing because you don't actually see the two-tail test playing out in it. That's why we do this one. So is this valid? Yeah. Yeah, it is. Even though we didn't find that number, it's valid because you're basically doubling the area so that you can directly compare it to alpha originally, if you understood that little nuance there. That's kind of important. Okay, so recapping before our conclusion, we find our claim and our opposite. You guys should be rock solid on that. We state one of them as h sub 0, that's the one with the equal sign. One of them is h sub 1, that's the one without the equal sign. We find our significance level, it will always be given to you. If it's not, it'll be 0.05. Okay, that's the most common one. Then we find our test statistic in either case. So steps 1 through 4 are identical with the p-value method, which this is, or the traditional method, which I'm about to show you in like 5 minutes over here. Make sure that when you're dealing with proportions, you have decimals. You shouldn't be plugging the whole numbers with proportions, and we can't do that. These things are all going to be between 0 and 1. We find our test statistic, and with the p-value method, what you do, you look at whether it's a one-tail or a two-tail test, either a left or right tail or a two-tail test, and you put the appropriate number of test statistics up there. If it's a two-tail, we've got to list it twice, one positive and one negative. We find the area in the tails, add it together if you have to, and compare that to alpha. If it's less than or equal to alpha, bam, we have enough evidence. If it's not, then we don't, and we have to fail to reject. So let's interpret what this means. Okay, let's interpret this. This says you failed to reject, and this is why we do this example, because it's way off, right? I mean, this isn't even close to alpha. There's not even nearly enough evidence to overturn it. In fact, this claim is probably true, but you're going to see that we can't prove it with this. Look what happens. We failed to reject the null hypothesis. That means we failed to reject this. We failed to reject this one. We failed to reject our claim. We failed to reject our claim. Does that mean the opposite is true? No. Does it mean the claim is true? Maybe, but we don't have enough. We don't have the evidence to say that. Do you see how when you state your claim incorrectly, or when you state it with an equals, you can't ever prove it right, even though this very well may be a true statement. It's 0.26. It's really close to 0.25. It's probably true, but the way it's stated is wrong. All right. So we wouldn't ever be able to prove that thing correct. We failed to reject the null. Right there. But that doesn't say that you accept it. It's like being guilty. It's like I'm using it again. It's like the guilty, not guilty. If you're not guilty, we just found it not guilty. Does that mean it's innocent? Does that mean it's right? No. No. If we had found it guilty, it'd mean the other one was right. This was definitely wrong. The other one's right. That's how our hypothesis testing works. So fail to reject. That's why we say if you fail to reject, you clearly say there's not enough evidence to state anything. Because even if you fail to reject your claim, it still doesn't make it right. It doesn't prove it right. It could be right, but it doesn't prove it right. So you'd say, no matter what, if you fail to reject, you'd state this right now. Put this on your paper. There is not enough evidence to support the claim that whatever you're stating. So there is not enough evidence if you fail to reject. If you reject, there is enough evidence. So it's either there is or there's not. That's the only two things you put on your paper. Right now, there is not enough evidence to support the claim that, and then you restate the claim. So on your paper right now, you should have, there is not enough evidence to support the claim that the proportion of yellow pods, that looks like poos, doesn't it? Yellow poos. Don't think too much into that one, is equal to 1/4. That's what you put on your paper. Now let's compare that to the traditional method. Not much is actually going to change. Here's what you do. From step number 4 on, it's different. But step 4, up to step 4, we're exactly the same. Here's step, actually this was step 5, I forgot that step. Here's step 5 for traditional. It's the picture step. You still have a picture, and you know what? It's still going to be a two-tail. Can you still identify that it's a two-tail test? Nudge your head if you can. Sure, it's still not equal to. So we still have a two-tailed test. The difference is the numbers that go here and here are going to be different than they were in the p-value. In the p-value, you use your test statistic here. In traditional, you use a critical value. Notice how critical value didn't even appear over here. Critical value is going to come here, where you put your alpha in your tails, and you find your critical value from that. So, question. How much is that? If you're talking about the traditional method, how much is that? Great, 0.025, because this is going the backwards way, right? Instead of comparing these areas directly to each other, we're comparing z-scores together. It's the same exact idea, just backwards. So this is 0.025. Where are we getting the 0.025? Why did we cut 0.05 in half? Ah. And then you got to be able to tell me what numbers go here and here from the 0.025. It's on your z-table. It'll be on your z-table. What'd you get? 1.96? How many people got 1.96 if you got a table? Good. All right. Do you see where they're getting the 1.96 from? We're looking up the 0.025. That's going to give us, well, actually, negative 1.96. So I know that's negative 1.96. And this one over here is 1.96. And that's a critical value. After step number 5, we compare now with the traditional method the test statistic to that picture. We got to determine where the rejection regions are and where the fail to reject region is. Which one is the fail to reject region? Is this the fail to reject region? How about this one? How about this one? No, these are your rejection regions. That's the fail to reject region. Let's see where we lie as far as our test statistics. Test statistic, that's hard to say, isn't it? Test statistic. Test statistic. Good thing you guys are not here because I'd be spitting all over you right now. Our test statistic is 0.56. Notice how you don't have to look up the area with that one. You just go over here, you go, okay, where is 0.56, which is a z-test statistic? Where does it fall according to our z critical values? We're comparing z's to z's. We're comparing areas to areas here. Z's to z's over here. Where's our 0.56 fall? Does it fall in our rejection regions or in the fail to reject region? That's like right here. 0.56. So that tells us right there, if we're in the fail to reject region, we have the same exact conclusion. You're going to fail to reject H sub 0. And we have the same conclusion, or the same interpretation. We have that there is not enough evidence to state the claim or prove the claim that the proportion of yellow pods is equal to a quarter. So the big difference here between, I've said it many times, I really want to make it sink in your heads, you have to know both. You got to know both. You got to know both because in order to do this with a t value, you got to know traditional. You got to know p-value because this is what most people do now, especially with z's. Why? Well, I don't know why. Maybe they think it's easier to compare your alphas. You got to know both though. So with our p-values, we're putting our test statistic on the table and looking up areas, adding them together if you have to, and comparing it directly to your alpha. This is the backwards way of doing it, kind of. You look up your alpha first in your tails. It'll give you your critical values, and you compare your z-score directly to that. So, are you looking up areas in either case? Yeah. Are you looking up z's in either case? Yeah. Yeah, you really are. Just depends on which one you prefer, or which one is given to you to do. How many people feel okay with this example? And the difference between a test statistic, I'm sorry, a traditional method and a p-value method, yes? All right. Well, that ends our 8.3. We've got 2 more sections. And you know what? They're going to be exactly the same, basically, as what we just did. So if you know the p-value method and you know the traditional method, you're set already. All right. Well, all we're really going to do is maybe do one example from 8.4, 1 or 2 examples from 8.5. Just go over this hypothesis testing a couple more times in the next 2 days. This is Monday, right? Okay. So we got 3 days to do a couple sections here, and then we'll talk about one more little thing. We'll talk about how to deal with variance and standard deviation and hypothesis testing.